Hi, this is question 4 from the AQA Further Pure for June 2009 exam paper. In this question we are shown that we've got a system of equations here and we need to show that it does not have a unique solution and is consistent. Okay, so we're showing two things. We're first of all showing that it does not have a unique solution, and we're also looking to show that it is consistent. Okay, so we will deal with the first part, showing that it does not have a unique solution. So hopefully you know that in order to show that it does not have a unique solution, we would want the determinant of this matrix to be equal to 0. So if I write it in matrix form first of all, so I would write this as 3, 4, 5, 1, 2, 4, and 3, negative 5, 14. Okay, so I've just written it in matrix form so it's clear what's going on. So if I multiplied this by this here, I would get this system of equations. What I'm looking to show is that the determinant of this part here is 0, and that will tell us that it does not have a unique solution. The reason why that works is that if this didn't have a determinant of 0, then that would mean an inverse matrix exists for this, so I would be able to pre-multiply that onto the other side and get a unique solution. If the determinant is 0, that wouldn't be possible because I can't do an inverse of a matrix where the determinant is 0, so that will tell us that there isn't a unique solution. So you don't have to write this part of it out in your exam. You can go ahead and just show that for part A I would just be showing the determinant of this here. Okay, I'm just working out the determinant of this bit here, and hopefully that will work out to be 0, and that will be showing us that there's not a unique solution. So so that's going to be 3 times 14, 20. And you can go ahead and pause the video and finish this off. 4 times negative 14 plus 12, and then I've got plus 5 times, I've got 5, take away 3, so that gives us negative 18 plus 8 plus 10, which gives us 0. Okay, so we've been able to show that the determinant of that is in fact equal to 0. Okay, I'm just going to just get rid of that. And I'm just going to put equal 0 there because otherwise I'm going to run out of room for the rest of the question. Okay, so we now need to show that it is consistent. So I'm just going to move this over here, and I now need to show that it is consistent. Now, in order for us to show that it is consistent, there's a few ways that we can do this. I'm going to go ahead and I'm going to write it in row echelon form. So I'm going to write this first of all as an augmented matrix. So I'm going to say 4, 5, -1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, Okay, so this is in augmented matrix form. And now what I can do is perform row operations to try and reduce a corner or a triangular corner of this matrix to zeros. So I'm going to aim to make this part of the system of equations 0. Okay, so I'm gonna deal with these two first of all, and then once I've dealt with these two, I'm going to aim to make that number there 0 as well. So in order to change that to 0, I would have to times it by 3 and take away 4 lots of my top row. So my new row 2, I would do 3 times my old row 2, take away 4 lots of the row 1. And I'm going to do the second bit in one go, so I'm now going to reduce this to 0. So in order to change that to 0, I would do 3 times this row and take away 5 times that row. So my new row 3 is going to be 3 times my current row 3, take away 5 times row 1. Okay, so I can now write down what the new matrix is going to be. I've not touched the top row, so I'm just going to write that out again. That's going to stay the same. Now this middle row, I need to do 3 times row 2 take away 4 times row 1, so that's going to be 12 take away 12, which is 0. I've got 3 take away negative 4, which is going to make that 7, and I've got negative 15 take away 12, which makes that negative 27, and I've got 51 take away 44, which is going to make that there 7. Okay, the bottom row, I'm going to do 3 times row 3 take away 5 times row 1, so 15 take away 15 is 0, 3 times that is negative 12, take away or plus 5, which gives us negative 7, and then I've got 3 times 14, which is 42, take away 15 is 27, and 3 times that there is going to be 48, take away 55 is going to be negative 7. And there we go. Right, so I now have got my 2 zeros here, so I can now use this row here to change this number here to 0, and you can see that I quite simply, to get my new row 3 now, I'm going to do row 3 add row 2. Yeah, because negative 7 plus 7 is going to be 0. Okay, so I've got 3, negative 1, 3, 11, because I've not changed the top row. I've got 0, 7, negative 27, 7, because I've not changed the second row. And this row here, 0 and 0 is 0, negative 7 and 7 is 0, 27, negative 27 is 0, and negative 7 and 7 is 0. Okay, so what's happened here is that I'm saying that 0x plus 0y plus 0z is equal to 0. Because that is possible, it's possible for me to times my x, y and z by 0 and get 0 as my solution. It has to happen, I guess. Then I would say that the equations are consistent. If that there would have been a 5, for example, or any number that wasn't 0, well then I wouldn't be able to do 0 times something plus 0 times something plus 0 times something to give me anything other than 0, so then it would have been inconsistent. That would have told us that there weren't any solutions that existed. But this here is now telling us that it's consistent, which means that there's an infinite number of solutions that exist. So our three planes will intersect and form a line. Okay, so that's the first part of the question. Another way that I could have done this, if I just move this over here, so it's with part A over there. Okay, another way that I could have approached this is, for the second part, is I could have spotted that if I did 3 times that equation and took away that equation, that would give me exactly this equation here. So 3 times 3x is 9x, take away 4x gives us 5x, 3 times negative y is negative 3y, take away y gives me negative 4y, 3 times 3z is 9z, take away negative 5z gives us 14z, and 3 times 11 is 33, take away 17 gives me 16. So that would also show that the equations are consistent. Okay, moving on to part B. So a slightly different scenario here. We've got a transformation of 3-dimensional space that maps points x, y, z onto image points x, y, z, such as this here. And we want to find the coordinates of the invariant points of T, so they're the points that don't change. Okay, so let's just think about what's going on. I've got a new point x that's going to be made up of my original point x, take away my original point y, plus 3 times my original point z, take away 2. My new point of y is going to be made up of this here, etc. Now, in order for me to find the invariant points, what I want to happen is I want my new point of x, where I take my old point of x, etc., to be exactly what it was to start with. I want my new point of y to be exactly what it was to start with, and my new point for z to be exactly what it was to start with, and that will tell me what the invariant point will be. So I can rewrite this, and instead of saying the image of x, I'm just going to say x. Instead of saying the image of y or the image of z, I'm just going to call that x, y, and z. And I want to carry out this transformation here. And I want to and I want these to end up back where they started. So I'm just rewriting this equation and placing the image of x, y, and z with just x, y, and z. Okay, so I can now write down 3 different equations, because I could say, well, my x coordinate must be equal to x take away y plus 3z take away 2. My y must be equal to 2x plus 6y take away 4z plus 12, etc. So I'm now going to write that down. So x is going to be equal to x take away y. This is question B, and y okay. Okay, right, so I'm now going to rearrange these equations to get them in a nicer form so that I can spot if there's anything that I can do to simplify them and solve them. This first one, I think I'm going to get, if I take x from both sides, and I'm going to add 2 over, so the first equation is now going to become minus y plus 3z is equal to 2. For the second equation, I'm going to get 2x plus 5y take away 4z is equal to negative 12. And the third equation, I'm going to get 4x plus 11y plus 3z is equal to 30. Okay, right. So those are my 3 equations. And I could now go ahead and write this in echelon form like I did before, and in augmented matrix form like I did before, and reduce it into row echelon form. But I can spot straight away that if I double this equation and took it off this equation, I will have eliminated my x's, and that will give me enough information to be able to go on and then solve them. So if I'm just going to call this equation 1, this one equation 2, and this one equation 3. Okay, so I'm now going to do 2 times, I'm going to do, take equation 3 and I'm going to take away 2 times equation 2. Okay, so equation 3 take away 2 times equation 2, that's going to make the x's disappear, and that's going to make that y, that's going to make that there 11z, yep, that's right, and that's going to make that there 54. Okay, so I've now got y plus 11z is equal to 54, and I've also got this equation here, which is negative y plus 3z is equal to 2. So I'm just going to call this one equation 4, so that I can now do equation 1, and I'm going to add it to equation 4, because that's going to make my y's cancel each other out. Okay, so that's going to make it 14z is equal to 56, and now I've got a solution for z, because z is going to be equal to 4. Now I've got my solution for z, I can stick it into here, so I've got negative y plus, and 3z is going to be 3 times 4, so it's going to be 12 is equal to 2. So that tells me that y is going to be equal to 10. And now that I've got y is equal to 10, I'm now going to stick that into one of these equations over here. So I think I'll choose that one there. So I've got 2x plus 5y, which is 5 times 10, which is 50, take away 4z, which is 4 times 4, which is 16, is equal to, and that's going to be negative 12. So that tells me that x is going to be 2x is going to be equal to negative 46, I make that, and that tells me that x is going to be equal to negative 23. So I've now got a solution for x, y and z. So I can write down my final solution as the invariant point is going to be equal to, and it's negative 23, 10 and 4. Okay, I'm just going to tidy this up. Right, so what we're saying is that if I carry out this transformation here on this point here, then that point would end up back where it started, and that's actually the only point that would be the case for. So let's just check on the first one. If I put negative 23 in for x there, and 10 in for y, and 4 in for z, I've got negative 23, take away 10, which gives us negative 33, plus 3 lots of 4, which gives us negative 21, take away 2 gives me negative 23, and the x coordinate ends up back where it started. You can check for yourself to see if that's true for the y and for the z, but it will be. And there you go. I will see you next time.